Alrighty, CP Physics has a test on Wednesday on work and energy. And the energies we're looking at in this particular chapter are the mechanical. Is that spelled right? Yeah, it looks like it. Mechanical energies, of which kinetic energy, gravitational potential, and elastic potential are the three we're focusing in on. Kinetic energy dependent upon the mass of the object and its velocity, with velocity playing a bigger role because of the squared factor. Gravitational potential relying on mass of the object, acceleration due to gravity at that location, and height, and we'll talk about how we measure height in a second. Elastic potential energy for springs and rubber bands, things like that. A value called the spring constant, which tells you how much force is required to produce a certain stretch or compression of the spring, i.e. how stiff or loose is the spring, and the displacement of the spring. Now these two are values of position, and so sometimes we call gravitational and elastic potential energies energies of position. When we are solving for these, kinetic energy and elastic potential must be positive. The reason is, regardless if I'm going to the left 10 meters per second or the right 10 meters per second, or 10 meters per second at an angle, the magnitude of those particular values is going to always square to be a positive number. I can't have a negative kinetic energy. The same thing with the stretching or compressing of a spring. Whether I stretch it 10 centimeters or compress it, and I'd have to call it negative 10, the same amount of energy would be stored. But for gravitational potential energy, it could be positive or negative. And the reference is where I measure height. If I have a ball, and I want to know what's the gravitational potential energy of the ball relative to the floor, we tend to call that height positive, and we call the gravitational potential energy positive. However, let's say I want to know it with relation to the ceiling. In that case, we call his height negative. He's below the ceiling, and the gravitational potential energy is also considered negative. So if you are above, right here, where we're measuring height from, your energy is positive. If you're below that, your energy is negative. Now, exactly from where we measure height, that's something I have to think about. There is no one true and only sort of reference point or zero mark for measuring height. It depends upon the question. So I could have a little desk over here, and again I'm holding that ball. Well, with respect to the floor, my height would be that value, and my ball would have a certain potential energy, with height being the distance ball to floor. However, if I just scooted the ball over, what's his gravitational potential energy relative to the table? Because if I drop him, that's where he's going to land. That's my height. So, for both of these, an MGH calculation would tell me what is the gravitational potential energy, but it's with respect to a certain location. Where do I start the zero to start counting upwards numbers of meters? And so I can pick any reference point I want. I just have to make sure it's clear which one I'm choosing. So if we look at some samples, for kinetic energy, you might have something like a car whose speed right now is 10 meters per second. It could be east, it could be west, it could be north, south, left, right, doesn't matter. His mass is 2,000 kilograms. And if I want his kinetic energy, 1/2 mv squared, 1/2 2,000 kilograms. My speed, 10 meters per second. Don't forget to square it. And I get 1 times 10 to the 5th joules. And joules is the unit for all energy. Kinetic, gravitational potential, elastic potential, electric, nuclear, doesn't really matter. Now, with kinetic energy, you could be asked to solve for mass, if you know kinetic energy and velocity, or velocity if you know mass and kinetic energy. Don't forget that for velocity, in the formula it is squared. And so on our calculator, we would have to throw in that square root answer keystroke in order to finally get velocity on his own. Now the other form of energy that is mass dependent is gravitational potential. We might have a tree and the height, 19 meters, has a little apple up there with a mass of 0.6 kilograms, and I want to know the gravitational potential energy. Well, being on Earth, I know my value for G, and so I'd go into my formula. mgh is gravitational potential energy, 0.6 kilogram. Our value for gravity, 9.81 meter per second squared, 19 meters of height, and I get 112 joules. Pretty straightforward, pretty simple to work with. The only one that doesn't involve the idea of mass, of course, is the elastic potential energy. If I had a spring with the spring constant of 8 Newton per meter, and I go ahead and stretch him 15 centimeters, how much elastic potential energy am I storing? Well, I do have a unit conversion I must deal with. I must turn him into meters before I can go any farther. And then I set up my formula. Elastic potential energy is 1/2 times the spring constant times displacement squared. 1/2 my 8 Newton meter, or Newton over meter, excuse me, 0.15 meters squared, and I get 0.09 joules as my answer. So calculating individual energy types goes pretty quickly. Now sometimes bits of information aren't given to you, for example, quite like that. They might say that our spring starts off at a position of, let's say, let's see, how would I draw him? Erase all this. I need a bigger eraser. Alright. My little spring is hanging down. And right now, let's say it's hanging down 3 centimeters. And I'm going to stretch him another 2.5. What do I put for delta x? I put 2.5 centimeters. Or maybe they just tell you a spring starts at 3 centimeters and I stretch him to a total of 5.5. What's my displacement? 2.5 centimeters. My 0 point for measuring position on a spring is something we call the relaxed length. And that is when I let a spring just hang, or if it's a horizontal spring, let him spring out as much as he's going to horizontally. That particular value, whatever it is where I start to measure displacement from. So if I now compress him so much or stretch him so much, that is my delta x. Compress him so much, stretch him so much, there's your delta x, or in this case delta y. It doesn't matter what that relaxed length actually is. I could have something, for example, I have one spring and I have another. You can kind of tell that one's a little longer than this one is. But if for him, I go ahead and stretch him 1.5 centimeters, and this guy, I stretch 1.5 centimeters. As I go into my formula, 1/2 kx squared, both would have the same x value. So it's not what the relaxed length is to start. That's actually irrelevant. It's what is the change. Now, when I'm dealing with the idea of a stretching or compressing of a spring, a speeding something up or slowing it down, i.e. giving it more kinetic energy, or reducing the kinetic energy, or if I'm lifting something up, or letting it fall down. All of those scenarios involve forces and displacements. In other words, they involve work. When we're dealing with the idea of work, there is something that we call the work kinetic energy theorem, which in truth could be broadened to a change of any form of energy. When you do work on something, you change the amount of energy it has. When it does work, it also changes the amount of energy the object possesses. So if I take a ball and I lift him above the ground, I did positive work on the ball. Why? Force was up, motion was up. Well, in doing so, I also gave him some potential energy. Take a spring and stretch it. Force down, motion down, positive work. Guess what? I added potential energy to the system. Take a car, hit the accelerator. Force forward, motion forward, positive work. What I do? I gave it some kinetic energy. And if I happen to wind up, instead of stepping on the gas, I stepped on the brake, brake in that direction. Well, in that case, I have my displacement in one direction, force in another. Negative work. And guess what? You lose kinetic energy too, because your speed went down. So work and energy, a change of one will match the change in the other. Positive work, add energy. Negative work, take away energy. And if we would do some problems with something like that, a couple of things to keep in mind. One, don't forget that net work, we're looking at net force times displacement. So you might have to first solve for net force, or if you're using a kinetic energy change to document a net force, remember that's what it means. You might not be able to go ahead then and disentangle individual forces. Sometimes you can if they give you one and you're looking for the other, but very often you might not be able to pick them apart. 2, keep an eye on signs. If you get a change of energy that's negative, it does mean negative work. If you get a change of energy that's positive, that does mean positive work. So let's look back at our car example we had, where our car had a kinetic energy of 1 times 10 to the 5th joules. He was going 10 meters per second. He's not quite a speed demon. Let's say, though, he slams on his brakes and now it comes to a stop. I have a force. I'm going to call it force of R because it is a combination, let's say, of the brakes, but also the friction between the tires and the road and air resistance. But 6,000 newtons is what acts on the car. And it does act in a reverse direction of the actual motion. I want to know, how far do I have to travel before I come to a stop? i.e., what's my stopping distance? This is a nice candidate for the work kinetic energy theorem. I know that I have a combination of forces that is going to move my object through a distance, and it is going to cause a change in the kinetic energy of the object due to the change of the object's speed. I know my force, I'm looking at about 6,000 newtons, and I'll make him negative, times my distance. He comes to a stop, therefore velocity is 0, and therefore kinetic energy is 0. Meaning that now as I go to put in my values to get the initial kinetic energy, which I already know, I don't even actually need to go through that, because we calculated in the earlier problem, 1 times 10 to the 5th joules. I'm going to have a negative kinetic energy on this side, which will match the negative work I'm going to have on this side. And having the negative kinetic energy and the negative force, I'm going to get a positive distance, which is what I should see, because I'm still going forward. Friction's acting that way, but I'm still going this way, so I better get a positive displacement. And I do, of 16.7 meters. This is how all the driver's ed books actually get stopping distances. What is the average force provided by the brakes on an average passenger car? What's the average friction between the average road conditions and the average tire configurations? Blah, blah, blah. They get average force of resistance acting on the car when you brake. Given highway speeds, how far do you need to leave between you and the car in front of you in order to be safe? Now, when all of a sudden it's icy or it's wet, this value is going to go down. We know that. But given the same kinetic energy change, going from one speed to the next, the kinetic energy change is not going to vary. If my force suddenly drops, I've got to have much more stopping distance so that the kinetic energy change can be met. And that's why on wet, slippery roads, we have to leave more space between us and the car in front of us in order to be safe. Now, one other thing I just want to throw in here, and I've seen this trip people up, and that is for gravitational potential energy. I have seen people have problems when objects have been pushed up hills or on hills or are going to slide down, something like that. The question becomes, if I put a ball up here at the top of a hill, and I want to know what is the gravitational potential energy. Let's say I have a hill that's 40 meters long at an angle of 20 degrees to the horizontal. When you go to solve for MGH, height is not 40 meters. Sorry, that was me rattling papers at my dogs. Gravity does not operate horizontally. Gravity only operates vertically. In a problem for gravitational potential energy, if you have to solve for something that's on a hill, you got to solve for that height. Because this is the height that goes into your formula. In this case, I would have 40 meters sine of 20, or 13.7 meters. That is the height. I don't care how long the hill is, none of that matters. What matters is that side. So if you have something on a slide, on a hill, on an incline, whatever it might be, a ramp, they'll give you the hypotenuse. You have to solve for height. But be very careful. If the problem does say you're on a hill with a vertical height of, in that case, they are giving you that directly. So be a little cautious on these. They can trip you up if you're not reading them very closely.